Okay, let's look at the next statement, E. Every set in the family has 3 elements. So is this true? So every set, okay, why is false?
This S sub 0 only has 1 element.
Okay, so good. So because, as I said, if you are claiming this is false, then you just need to provide a counterexample. So in this case, if you look at S sub 0, this is by definition 0 plus or minus 0. But as we know, we don't duplicate elements in a set. This is just a single element. Of course, this S sub 0 doesn't have 3 elements. Okay, this is E. So if Sn is a subset of Sm, then n is equal to m.
False. False.
Okay.
And n could equal 0 too.
Okay. All right. So this is a okay. So this is false. You still use the example counterexample. So the counterexample is S0 is equal to 0. So in particular, it's containing any Sn. But of course, you just pick any n, then which is different from 0, correct? Okay, so another example, another counterexample is you can also use B. If you use B, you can see S2 is equal to S negative 2. But so S2 equals to S negative 2, you can also say S2 is a subset of S negative 2. So in this situation, 2 is still different from negative 2. Okay, so you can either use S0 or two numbers which are negative of each other. Okay, let's look at the G. So for any n and m in Z, Sn intersect Sm equals to 0. Is it true or false?
False.
I could guess it's false.
False.
Because that's one that makes the most sense to me.
Why? Why is false?
Because when you take the two sets and their intersections, you'll have 0, but you'll also have other numbers as well. It's like a -1 or a -2 or a +1.
Well, if you have a claim in this, I would say, for example, if you look at S1, this is 0, 1, -1. S2 is 0, 2, -2. So what is their intersection?
0.
Yeah.
Oh, I see. You're saying Sn intersection Sm equals that. I see. So that would be true.
So is it true or false?
So their intersection is 0, so that will be true. Yes.
Okay. You claim
It's False. If you look at like S sub 1 and S sub negative 1.
Okay, good. Actually, this is still false, but the reason is because you also you heard that he said the S sub 1 and S sub negative 1 is the same as we have S2 and S sub negative 2, right? Because S2 and S negative 2 are both equal to 0 to negative 2. So if you look at this, then, okay, let me write here. So S2 intersect, say, S negative 2 is just equal to 0 to negative 2, because both sets are just equal to 0 to negative 2. All right, so this is false. All right, and let's look at the last statement we're going to look at for this problem. For any n m in Z, Sn intersect Sm is not empty.
True.
Okay, true. So Luke said it's true. Everyone agrees?
I do have a question.
Yes.
So say for instance, if you have Sn and Sm equal the same, say for instance they equal S negative 1, well S1, wouldn't the set become empty?
If you get, for example, S sub 1, S sub negative 1, if they're the same sets, their intersection is just a whole set, right?
Okay, so I was thinking of it backwards, well, in reverse. So okay, I was thinking that if they intersect each other, then
Okay, so
empty. Okay.
So the last one, the answer is true, because for each n and m, you know, this 0, this element is always in Sn intersect Sn. All right? For any two sets Sn and Sm, 0 is always in the intersection because 0 is containing both sets. So of course, this implies their intersection can never be empty, because at least contains 0, correct? All right, so this is the first problem. Okay, let's look at a second problem. This is also determine whether the following statements are true or false. Okay, for this case, we are for n be a natural number, our set Sn is defined to be negative infinity to negative 1 over n union 1 over n to infinity. Okay. So the first statement is n equals to m implies Sn equal to Sm. Is it true or false?
Yes.
Yes, okay.
True.
Yeah, it's true because if the subscripts are the same, then the sets are defined to be the same sets. Of course, they are equal. So this is clearly true, okay? So let's look at B. Sn equals to Sm implies n equals to m.
I think so. I think it's true.
Okay, you think it's true. Why?
I'm trying to figure it out.
Yeah, I'll give you a little bit more time to think about it.
I say it's false
Okay, you said it's false. Why?
because if you do the negative one, then n and m won't be the same.
All right. So one thing is good for you.
Natural numbers. I'm sorry, I forgot about that.
So you want to use the same example as last time, but remember here, our n is natural number.
Right. Yeah. Back to the drawing board.
Okay, but anyway, that's good. You remember the kind of example last time. So
Yeah, if it's natural numbers, I agree, it's true.
okay, yes, actually this is true because in this case, you are not allowed to use the negative numbers. So if two sets are equal in this case, then you can see because each set Sn is divided to two parts. One part is the negative part, the other part is positive part. They do not intersect. So once Sn equals to Sm, then both their positive parts and negative parts are going to be equal. This forces n to be equal to m. So the second statement is true. All right. So in this case, so you can see the range of the index set is important. You have to look at the range for the subscripts. So this is B. So let's look at C. And n less than n implies Sn containing Sn.
False.
False. Why?
If we have n be 1 and m be 2,
Okay,
One-
M1, MB2.
1/2 is in S sub m, but not in S sub. Oh, I'm bad. It's true.
Okay.
Switch the subset symbol in my head.
Okay. All right. So actually this is true. Let's see why this is true. So we do have to prove it. So let me write a proof here. So you can see so always remember this n and m are natural numbers. So if n is less than n, then you can see 1 over n would be greater than 1 over m, right? And also you have another thing is negative 1 over n is less than negative 1 over n. So the first thing would imply 1 over n infinity is contained in 1 over n infinity. So the second tells you negative infinity to negative 1 over n is contained in negative infinity to negative 1 over n. So in other words, the positive part for Sn is contained in the positive part of Sm. The negative part of Sn is also contained in the negative part of Sm. So this altogether implies Sn is containing Sn. Okay. But of course, this uses the condition Nm are natural numbers. So you get those inequalities because n and m are positive. So this is very important. So for this problem, the positivity of those subscripts are essential. Okay, D. So every set in the family is non-empty.
True, but I don't sound too confident, but true.
Okay, true. So everyone should agree this is true because no matter what the subscript n you pick, these intervals are never empty because no matter how big you are, this infinity is always greater than 1 over n, and negative infinity always going to be smaller than negative 1 over n. So both intervals are non-empty. So this one is true. It's clearly true. Okay. Now let's look at E. E is the intersection of the Sn. All the intersection of all the Sns is equal to the empty set.
True.
True. I heard true. So everyone agrees.
Yeah, true, because both halves of the union cancel each other out. So the sum of all of them should be empty.
Okay, so everyone agrees, but let's try to write a few sets. So what is S1? This is negative infinity to negative 1 union 1 infinity. So what is S2? This is negative infinity to 1/2 union negative 1/2 union 1/2 infinity. What about S3? Negative infinity to negative 1/3 union 1/3 infinity. Let me write one more. So what is their intersection? For example, let me ask you one question. Let's look at a particular number. Say the number 2. Is 2 contained in each Sn?
Yeah. Everything greater than 1 or less than -1 is in all of them.
Okay, everything greater than or equal to 1 or less than or equal to -1 is going to be, okay, everything is greater than 1 or smaller than -1 are going to be in every set, right? So what is their intersection?
S1.
Great, great. Yeah, that's the answer. Actually, their intersection is not empty. Their intersection is just S1. Actually, if you observe carefully the statement of C, so the statement of C tells us if the subscript is larger, if M is greater than N, then Sn is a subset of Sn. In other words, as the subscripts increase, the sets becomes larger, right? So S1 is going to be the smallest set, and S2 is larger, S3 is even larger. So as the subscript increases, the set becomes larger and larger. So the first set S1 is going to be the smallest. It's contained in every set bigger than when subscript is bigger than 1. So because of this, we know this actually this intersection is equal to S1. All right. Okay, so here, this is force because the intersection of Sn as n is in N is equal to S1, which is negative infinity to -1 and 1 to infinity. Actually, to show this statement is force, you just need to say, you pick any counterexample would be enough. You just say the number 2 is containing every Sn. Then of course their intersection cannot be empty. All right. So this is a non-trivial problem. So let's look at F. For any n in N, 0 is not in Sn intersect Sn.
True.
Okay, true. Everyone agrees?
Yes.
Okay, true. So can you explain why?
I really can't. I see it in my head, and I got a picture of it, like the line of a graph, and then the two intervals right there. But 0 is not a part of those intervals, and they don't intersect. It doesn't. It's not an intersection of those intervals on other numbers as you go up.
Okay, so you have an intuition. However, you don't formulate the proof correctly. So remember, in our course, you do want to write down your reasoning, okay? Intuition is not enough. Intuition is is an important step, the first step. However, you need to write down why, rigorously, why this 0 is not there. So actually, I can even get a stronger statement. 0 is not containing any set Sn. 0 is not in any Sn. Of course, it cannot be containing the intersection. So you can see this 0 is not in 1 over n to infinity. And 0 is not in negative infinity to negative 1 over n. So these two conditions would imply 0 is not in Sn for any n. Correct? So you show actually 0 is not containing any set, so it cannot be containing the intersection. So this is just the reason. All right. So if x is not equal to 0, then x is in the union of Sn.
True, because 0 is the only one that's found to not be in the union.
All right. Everyone agrees? Okay, so the answer is correct. This is true. But we have to give a rigorous proof. All right, so here is the proof. So if x is not equal to 0, then either x is positive or x is negative. So we have two cases. All right, two cases. And the first case, if x is greater than 0, by the Archimedean principle, so there exists a natural number n such that 1 over x is less than n. Okay, because x is positive, 1 over x is positive. So we just find that n is greater than 1 over x. So once n is greater than 1 over x, we know that x is greater than 1 over n. Hence, we know that x belongs to 1 over n to infinity. And but Sn, this is just a positive part of n, and x belongs to Sn. Okay, because 1 over n to infinity is just the positive part for Sn. On the other hand, the second case, if x is less than 0, again, by the corollary of the Archimedean principle, okay, there exists an m in Z such that m is less than 1 over x. So this tells you, but you should remember in this case, x is negative. So this inequality actually tells you x is less than 1 over m. Okay, so this implies what? Hence, x belongs to negative infinity to one over m. But you should remember this m is a negative integer because m is less than 1 over x. 1 over x is a negative number, so m is a negative integer. But this is containing as, well, you should be careful, negative m. Okay, m is a negative integer, so negative m is going to be a natural number. All right, so let's come here. M is negative integer. So this negative m is a natural number, belongs to n. So that's why this set S sub negative m is well defined. All right. Okay, so in either case, x either positive or negative, you can always get a subscript n or negative m so that x belongs to the set as n or as negative m. So essentially this tells you x is in the union of Sn. All right, so you can see when you prove this set containment involve natural numbers or integers, the Archimedean principle and the corollary of the Archimedean principle is essential. Especially you want to get some control, some inequalities, you have to use the Archimedean principle. Okay, so now let's look at a few more examples. We go to more details of the proof. So because this is one of the proofs we have to understand. Because in our exam, those kind of problems will certainly be tested. So the first problem is to prove that the union from negative n to n with n in n is equal to the set of all real numbers R. So always remember, if you want to prove two sets are equal, you have to first prove the left-hand side is contained in the right-hand side, and then prove the right-hand side is contained in the left-hand side. And how to prove one set is a subset of the other. You just take an arbitrary element in the set, you show this element is so containing another set. All right, so let's follow the two-step proof. We first show that the left-hand side is containing the right-hand side. To prove this, we'll take an arbitrary element. Say, let X be in the left-hand side in the union. Okay, so then you have to use the definition of union. X is in the union means X belongs to one of the intervals. Then X belongs to some intervals for some and 0 in N. And then this is, of course, because the whole interval, so it belongs to R, so X is in R. So this is clear because the whole interval here is in R. All right, so one direction is easy. So this is step 1, okay. So step 2, we prove that the right-hand side is containing the left-hand side. So in this case, we'll take an arbitrary element in R. So what we are going to use is, of course, the Archimedean principle and its corollary by the Archimedean principle and its corollary. There exists a n in N, a natural number, such that X is less than N and greater than negative N. Okay, so although the Archimedean principle just tells you the upper bound and the corollary tells you the lower bound, but we did prove a problem which says that we can pick the same natural number N so that N and negative N serve as both the upper bound and lower bound, okay? So you can use this statement in your exam. So X belongs to negative N to N. Hence, X belongs to the union of negative N to N with N in N. So once you finish the proof of these two steps, you can claim, therefore, the union of negative N to N in N is equal to R. Okay, so I think this is a simple problem. Now let's look. Prove that the union of the open interval 0 to N over N plus 1 with N in N is equal to the open unit interval 0, 1. Okay, so let's prove it. Still 2 steps. So step 1, we show that the union of 0 to n over n plus 1 is contained in 0, 1. To show this, we take an arbitrary element in the union. Okay, by the definition of the union, we know that X belongs to the union, belongs to one of the sets. Zero, sum n0 over n0 plus 1 for sum n0 in n. So this means x is greater than 0 is less than n0 over n0 plus 1. But since n0 over n0 plus 1 is less than 1, so what we have is actually x is greater than 0, less than 1. Hence, x belongs to 0, 1. Okay, so this finished proof of the first step. Now let's look at step 2. We prove that 0, 1 is contained in the union 0 to m over m plus 1 with n in n. So to prove this, we take an arbitrary element in the open interval 0 to 1. Okay, so x is in 0, 1, then this tells us x is greater than 0 and less than 1. Okay, now here comes to the tricky part. What you wanted to do is to find a natural number n so that n is less than n over n plus 1. So you should try to understand what does this mean. If you want n is less than n over n plus 1, then that means 1 minus x would be greater than 1 over n. So what we are going to do is by the Archimedean principle, there exists a natural number n0 such that, well, the key here is less than n. Okay, you can see this quantity here. So I'll explain why I choose this quantity later. And now let's try to finish the proof first. then I'm going to come back to explain why I choose this quantity. Okay, so if you remember, x is less than 1, greater than 0, so you know this number is a positive number. Positive number. So what you get is, if you multiply 1 minus x, so you get 1 is less than 1 minus x times n 0. And if you then divide n 0, then what you get is 1 over n 0 is less than 1 minus x. So this implies what? You move x to the left-hand side, you get x is less than 1 minus 1 over n 0. But this implies because 1 minus 1 over n 0 is exactly n 0 over n 0 minus 1 over n 0. But if you write one more step, so what you get is x is less than n 0 minus 1 over n 0. But this is less than n 0 over n 0 plus 1. So you understand this step? N 0 minus 1 over n 0 is less than n 0 over n 0 plus 1. Okay, so this implies what? This implies x is greater than 0, less than n 0 over n 0 plus 1, which implies x belongs to 0 and 0 over n 0 plus 1. Okay, so x belongs to one of these intervals. In particular, this implies x belongs to the union of 0 to n over n 0 plus 1 with n in n. So therefore, these two sets are equal. Okay, so you can see from this argument why we choose 1 over 1 minus x is less than n 0 is because this inequality eventually gives you that x is less than n 0 over n 0 plus 1. So this is the reason why we need to choose this. But of course, when you try to figure it out, when you try to figure out how to get this quantity, what you do is, so thinking, okay? This is how you think about it. So you want actually x to be less than n over n plus 1. This is what you want. Then you solve it. So this is nx plus x is less than n. And then what you get is this x over 1 minus x is less than n. Actually, this is the exact thing you want to use. So you just need to pick n which is greater than x over 1 over x. But in here, I choose another way, which makes it stronger. But anyway, the exact condition is if you pick an n which is greater than x over 1 over x, then this would give you this one. But this is exactly what you want to find. You want to find an n so that x is less than n over n plus 1. Okay, so I wish you could try to figure it out after class, because this is a key for the proof of this example. So in some of the problems, it is always a case you want to figure out how to find out the right n to dominate the quantity you want. Okay, let's look at one last example, then I'll let you go. So prove that the intersection of 0 to n plus 1 over n, this is equal to 1, 0, 1, with 1 included. Okay, again, we need to follow 2 steps. So step 1, we show that the intersection is containing 0, 1. Okay, to show the intersection is containing here, you need to take an arbitrary element in the intersection. So to show this element is in 0, 1, you just want to show it's always greater than 0 and less than or equal to 1. Okay, since x is in the intersection, then we know that x is greater than 0 and less than n plus 1 over n for all n in n. So in particular, x is greater than 0. So the key is to prove x is less than or equal to 1. So how to prove x is less than or equal to 1? We want to prove by contradiction. Suppose x is greater than 1. Okay, then by the Archimedean principle, there exists a natural number n such that x such that 1 over x minus 1 is less than n, okay? Because x is greater than 1, x minus 1 is a positive number. So what does this mean? This means 1 is less than nx minus n. Okay, so this implies when we do a computation, we know that n plus 1 is less than nx, and you divide the n, you get n plus 1 over n would be less than x. But this is a contradiction because you know that x is less than n plus 1 over n for every n. So this contradicts with 0, x between 0 and n plus 1 over n. This tells you x cannot be greater than 1. Hence, x is less than or equal to 1. All right. So x belongs to 0, 1. Okay, x is always greater than 0. Okay, step 2. We prove that zero, 1 is containing the intersection. So this is an easier step. So we'll let x be in 0, 1. Then we have x is greater than 0, less than or equal to 1. Okay, but since n is a natural number, then we know that 1 is always less than n plus 1 over n. So you can claim that x would be always less than 1 over 1 n plus 1 over n, because x is less than or equal to 1, but 1 is less than n plus 1 n. Hence, x belongs to 0, n plus 1 for n for all n in n. So x belongs to the intersection because x belongs to such interval for all n. So now we finish the proof of these two steps. So we get therefore these two sets are equal. Okay, so do you have any questions? All right, so one key thing, as I mentioned a couple of times, please try to figure it out. So the proof I left just now in the example, why I pick those numbers. The reason is just I want to find an n which satisfies the inequality. So in each of these examples, the key is always, for example, here, why I find an n satisfies this. This is again because we want this condition to be true. So we want that condition, so we reverse this inequality to get what we want. So when you work on this problem, you would work on your scratch paper to find out what condition you want, and then you reverse this condition to get the quantity which you can use the Archimedean principle. Okay. All right. So if you don't have any questions, then we'll stop. Yes.
Will you have office hours tomorrow?
Tomorrow?
Friday?
No, I don't have office hours tomorrow. So
I'm probably thinking of my other class. Can I schedule a meeting with you for tomorrow?
So you are meeting with me about just math problems or something else?
For the homework and today's class.
Okay, so let's say this, okay?
Okay.
Here's the plan. I think next Tuesday I'm gonna send an email. Next Tuesday I'll probably give you a review for the second exam. Okay. So as last time, we'll have half class time left over for homeworks or the questions. And also next Thursday, there will be just a question session. So you can ask all your questions. So there will be, next week will be essentially for review and questions. So
And then the Tuesday after that, we'll have a test.
yeah, the Tuesday after next will be a test. But
Okay,
I'm going to send out the exact schedule by email, all right?
Okay, thank you. I probably mixed you with my other class.
Okay, all right. All right, so I'll see you Tuesday.